In my practical bioinformatics series, I talk about tools and techniques of bioinformatics that I employ for my research projects. Hello, I'm Arpita Banerjee and welcome once again to my channel. In this video, I'm going to talk about energy trajectory of the receptor upon docking of ligand. And I'll compare rigid docked pose with flexible docked pose. So this is only just a little part of all the work that I did for my first rotation in the time frame of August 2018 to November 2018 at Stony Brook University. For my work here, the molecule that I worked with is crystal structure of human adipocyte fatty acid binding protein in complex with its ligand. The PDB ID is 2NNQ and the software I used is DOC version 6. So the PI of the lab, the principal investigator of the lab where I did this rotation, he asked me to take it easy and go around. I'm glad that I listened to myself and I chose to work. Otherwise, I would not have material for the video which I'm making today. As I got started with my rotation, I was introduced to students in the lab and they told me in which directory to find what script file to run the program. They have a wiki page which tells you the flow, like it tells you which should be the input file at first and then which output should you take to consider it as your input for the next round of running. As I started working, I realized that there was flaw in some of the inputs and outputs, and I mentioned it to the students over there, after which they corrected their wiki page. Okay, so this is the page I was talking about, and it seems some of these links are inactive. If I go to 2018 doc tutorial, it deals with the file, the PDB file 2NNQ, which is why the work which I did was on 2NNQ. And here are the steps of going about the docking. And say, for example, in generating spheres, you see the input is INSPH and the output is OutSPH. And obviously, for the next round of running, you would need this particular file and not anything else. For energy minimization, they're preferring to minimize the ligand to remove unfavorable clashes because they're supposed to affect the rigid docking, because as far as their methodology is concerned, the ligand will be docked as it is, as the complete ligand. Whereas in case of flexible docking, the ligand will be broken into fragments and the ligand will be built step by considering favorable orientations and torsion angles after each fragment addition. What I'm going to present today to you is the analysis which I did by myself. So the analysis part was neither initiated by them nor guided by them. This is the PDB entry 2NNQ, and that's how the molecule looks like. The red dots which you see are crystallized water molecules, and you see the ligand in pink, which is at the core of this green receptor. You download the protein ligand complex from PDB, you separate the receptor and the ligand, and then you add protons and charge to the protein and to the ligand as well. And then I energy minimize the ligand. The energy minimized ligand actually does not vary much, as you can see here in this picture, and the RMST is also very low. It is ideal to do energy minimization of the receptor. I docked the prepared protein receptor with the prepared ligand. Preparations of the receptor and the ligand was done in Chimera. And there are two ways of docking it: rigid docking, flexible docking. There are different scripts within the software for going through these two different protocols. And then finally, I compared the rigid docked pose with the flexible docked pose via footprint plotting. You use this footprint.in script where your feed is either the rigid docked pose or the flexible docked pose, and your reference is the crystal structure. So essentially, you compare the crystal structure with your docked pose or your docked molecule. Okay, so here I have crystal versus rigid dock pose on the left and crystal versus flexible dock pose on the right. And if you notice, the overlap between the structures is better on the left, as is also evident from the RMSD, the root mean square deviation, which is lesser, 0.619 Armstrong, as compared to the RMSD of 1.151 Armstrong of the flexible docking. So the deviation is getting higher when it comes to flexible docking. This is because when you dock a molecule flexible, there are adjustments made to make the molecule comfortable. So the bond lengths, bond angles, the rotations of the torsions, everything are adjusted to make the molecule have favorable interactions, and which is why they deviate a little more to fit comfortably. And that is what you see over here. Now here's a quick key for you to understand whatever I'm going to say later down. I have the docked ligand pose shown in blue and the crystal ligand pose shown in pink. This is how you will see the ligands in all the pictures. Whenever anything else apart from the ligands is shown, it is a protein residue. Like here you see on the right, it's a protein residue valine, whose energetic interactions with the ligand gets plotted. This is the footprint plot which plots the van der Waals energy interactions and electrostatic energy interactions of the ligand with the protein residues. Valine and its corresponding energetic interactions with the ligand is marked here by the green arrow. In this plot, the blue line is the van der Waals energetic interaction of the crystal structure ligand with the receptor, and the red line is the van der Waals energetic interaction of the docked ligand with the receptor. So this is how the interactions will be denoted all throughout. Just a plot on top, the van der Waals energy plot. You will see there are places or there are residues where there's a marked difference between the energies. The energies of the crystal structure and the energy of the docked pose do not exactly match at certain points. Say for example, ALA36 is showing a very sharp difference. You see the blue is shooting up as compared to the red, which means the docked pose is far more comfortable than the crystal structure pose. And if you go along the graph, there's also another point at tyrosine 128 where you see a marked deviation. Now, if I go back to the molecular interactions where these deviations are being noticed, here. So the pink one here is the crystal structure and the blue is the rigid dock pose. Now, here is the alanine 36 down on the left, and tyrosine 128 is on the right. Okay, I have just done away with all the residues, so I'm just showing the interactions which are relevant here. So if you see, in case of alanine, what's happening is the rigid docked pose or the blue pose has moved away a bit, which has reduced the van der Waals clashes. You see this difference over here at the plot. As far as tyrosine 128 is concerned, again, see the pink molecule is close by. It's closer as compared to the rigid dock pose. So what happens is docked pose is actually moving away from tyrosine 128, which is reducing the van der Waals clashes. It seems though that the deviation in ALA is much more. Now, what's happening with valine 115 when it comes to van der Waals energy? In case of valine 115, which is marked here with an arrow, it is noticeable that docked pose actually has higher energy. So the crystal structure actually is more stable. So what's going on? Valine 115 is on the right here. If you notice, the crystal structure, which is in pink here, is further away than the docked pose. Okay, so the van der Waals clashes for the crystal structure is lesser. Notice these areas where I'm hovering my cursor. So you can see very clearly that the docked pose is nearer, disposed to have more van der Waals clashes. Now shifting our focus to the electrostatics energy plot, which is down below, you will see that there's a marked difference at arginine 126. Here, I'm talking about this residue. So what's going on over here? Let's take a look at the molecular interactions. I have just the arginine residue shown here. The crystal ligand structure is in pink and the rigid docked pose ligand structure is in blue. And again, if you notice that there's a deviation between the structures where the rigid docked pose has actually moved away a bit. So if you follow my cursor, if you look at the carboxyl groups of the ligand, the rigid docked pose, it has moved away from this NH as well as this one over here. So the electrostatics energy, it's not as better as what it was in the crystal structure, which is why you see that arginine 126 of the receptor is less stable with the rigid docked pose as compared to the original crystal structure. Shifting to flexible docked pose. So here are two plots I have, van der Waals energy and electrostatics energy. The trajectory of energy difference between the residues as you go along the protein chain. Now, going back to crystal versus rigid, here are the plots, and here are the plots for crystal versus flexible. So take a look. Do you see any difference between this and this one? I think a major point of difference is over here in the electrostatics energy for flexible docked pose, here, right where I'm hovering my cursor, and this maps to arginine 106. One point of difference here in the rigid docked pose pointed out by the arrow in the graph below, and 2 points of differences pointed out by arrows in the flexible docked pose, again in the electrostatics energy plot below. Which is why I spoke of one interaction in the crystal versus rigid comparison, interaction with arginine 126. And I'm going to talk about two interactions here, interactions with 106 and 126. So what's going on here with R106 and R126 in the flexible docked pose? If you compare the crystal ligand with the docked ligand, you will see that the orientation of the ligand in the crystal structure is such, the orientation of the pink colored ligand is such that its carboxyl group can interact with the terminal NH2 group of R126 and the NHE of R106. So follow my cursor here. I'm talking about this one over here. So this carboxyl can interact with NH2 group of R126 as well as this NHE of R126. Another of the oxygen atom of the carboxyl group of the crystal ligand is oriented towards NHE of R106 to make favorable electrostatics interaction. Whereas in case of the docked ligand, the carboxyl isn't facing R106 to have an electrostatic interaction with the residue. Docked ligand's carboxyl group is primarily oriented towards R126 NH2 group, absolutely turned away from R106, which is why interaction with R106 is lost altogether. And that's what you see in the graph. See, the red is the docked pose and its energy at R106 is higher, so it is less stable, and that's because of the loss of interaction with arginine 106. Here if you notice the plot above, the van der Waals energy plot of the rigid docked pose, and compare it with the van der Waals energy plot of the flexible docked pose, there's a much more variation when it comes to valine 115. So what's going on? The docked pose has moved much closer, sort of like jutting out. So the van der Waals clashes is increasing, which is why here for valine 115 you see that the docked pose, the red line, has higher energy. It is less stable because it is moving way much closer to valine 115. So what's happening with the rest of the residues which show deviation in the flexible docked pose? They have a very similar profile as in the rigid docked pose. Alanine 36, it is closer to the crystal structure. So the docked structure is actually moving away a bit. And the same applies for tyrosine. You see the pink one, the crystal structure is closer as compared to the blue one, which is moving away here. So with respect to tyrosine 128, this structure, the blue one, is much more away, reducing the van der Waals clashes, right? And the same applies for alanine, but at a much lesser scale, I would say. In the plot, ALA 36, however, shows much more deviation as compared to tyrosine 128. Now, if you noticed a footprint plot of the docked complexes, you would see that both in cases of the rigid docked pores and the flexible docked pores, when they're matched with the crystal structure energies, you would see that there's a sharp difference at ALA 36. So this is what I'm talking about, the green arrow. ALA 36 shows a very sharp difference. Now there are two factors which needs to be mentioned in this regard. First, minimization of the crystal receptor structure is important because often when the structures are submitted, there's not enough of refinement done, and so there are clashes in the structure itself. So it is always better to minimize this crystal before even you do molecular dynamic studies or docking studies. The second factor is scoring correctly. So what do I mean by scoring correctly? Let's say here I'm talking about the van der Waals energy in particular. So van der Waals scoring is dependent on factors such as repulsive van der Waals forces, attractive van der Waals forces. Repulsive van der Waals forces is when the fluctuating polar charges, they'll repel each other. Say, for example, CH3 of ALA 36 and the CH of the ligand. This is what I'm talking about. Just follow my cursor. So the CH3 of ALA 36 and the CH of ligand, they would have repulsive van der Waals forces, attractive van der Waals forces. Example of that is hydroxyl of tyrosine 128 and CO of the ligand. Proton of the hydroxyl would have polar positive charge, as you can see here, and the oxygen of the carboxyl would have polar negative charge, and they are supposed to attract, right? So this is what I'm talking about. So follow the cursor. The OH of tyrosine 128, the proton in particular of the hydroxyl, would attract the carboxyl, the oxygen, the polar negative oxygen of the carboxyl of the ligand. It's a combination of all these forces which actually determine the van der Waals score, and that is what is supposed to get reflected here. Now, why bother about all these things? Because they have applications in virtual screening of chemical compounds. Say you're trying to find an inhibitor for a pathogenic protein, you're trying to design a drug, then all these things count. Scoring that you get from docking and ranking of the compounds have sort of this inverse correlation. So the more negative the score is, the higher the ranking of the compound, right? Now, if the scoring is not correct, then you can well imagine that your ranking won't be correct. You won't be looking at the compounds you're supposed to look at. If you rescore, then the order of the compounds may become like this. Okay, so scoring is important, and for that, correct balancing of forces is also important. Like I said before, there are certain things that needs to be checked. You cannot just totally and blindly rely on computers. When I was presenting these results to the lab PI in the lab, where the other lab members were present, the PI just diverted the discussion off to something else. So that's all for now. I'll make the next video when I will have time. See you later.